I'll update that, but I am the same person, and I'm psyched to be presenting here and talking about model training with PyTorch and AnyScale. So before I even get into the schedule of what we'll be doing today, I want to give a really, really high level of what is Ray, what is AnyScale, because I understand there may be people who have never heard of these tools, but thought, oh, well, maybe I'll check this out, or maybe you've heard of these. Or maybe even looked at them in the past, but you're not sure where things have gotten to here in 2024. Or just want to get a little bit more orientation. So before we go anywhere else, what is Ray? Ray is an open source project which represents the simplest, fastest way to build and deploy scalable computation. You can do all kinds of scalable computation with Ray. We're going to be focusing today on AI model training. And in general, these days, we're focusing on AnyScale as a firm is focusing on customers that are interested in life cycle for AI applications. So data processing for AI, things like featureization, vectorization, ingestion, pre-processing, model training itself. So probably the most famous model in the world that's been trained with Ray is GPT-3, GPT-4. So if you were at Ray Summit a year or two back, you may remember hearing about how OpenAI uses Ray to train their biggest language models. Of course, you can also use Ray for lots of smaller things that are not at that same scale. And then model serving. So that's what we're focused on for the most part today, but you can do all kinds of scalable compute with Ray. Where does AnyScale fit into the picture? So Ray is open source. AnyScale, and we'll talk more about AnyScale in just a minute, but at a high level, is an organization created by founded by the creators of Ray, and it's all about extending Ray in a number of dimensions. So even better performance. We think Ray is actually really, really highly performing by itself, but it's nice to have some funding that can go towards R&D, towards really, really pushing the limits. Adding more functionality, right? Just making the framework able to do more things. Usability, making it easier to do stuff. And then operations best practices. So all of those things that you need to do in between using a great open source library and deploying something in production in an enterprise. If you've been doing this for a while, you know that there's a lot of complexity in between those things, right? If we could just go from an open source library to putting stuff in production and have it work, that would be a nice world. But in reality, it's a little more complex, and so we need some more infrastructure there. And so all of those areas are places where AnyScale is adding a ton on top of Ray. I also want to make sure that I mention Ray Summit in San Francisco this fall, September 30th to October 2. If you want to learn more about Ray, more about AnyScale, if you want to meet the team, if you want to see all kinds of companies from around the world that are using the platform to do interesting things, that would be a place to check out. And I think those tickets are already on sale. Okay, so with that really quick kind of intro, let's talk a little more about what we're doing here in this tutorial today and a little more about AnyScale, and then we'll get into some code. So the virtual AI tutorial format is basically a webinar format. We've got about 1 hour together here today. I'm going to be demonstrating running actual code. So the code I'm running will be in Jupyter Lab notebooks, so not slides, and I'll be actually running it live on a Ray cluster on AnyScale. You can try this workload yourself, not kind of synchronously as I do it, unless you're already set up, but you can definitely do it on your own because we've got a self-service version of AnyScale you can sign up for directly today and start using it right away without a credit card or anything. There's some compute credits built in there. So if it's interesting, you can start running code like this and testing stuff out right away. So 100% runnable code. We're going to look today at some model training workloads, and then maybe in other sessions, we'll look at some other ones. And in some sessions, we'll talk about fundamentals of scalable compute for AI. So that'll come in from time to time, but I don't want to get too academic on that stuff. And then live Q&A, so any kind of questions. So it looks like somebody has their hand raised. And for this kind of a format, because we're a little tight on time, I would say just go ahead and put questions into the Q&A, and we'll kind of address those there. Just because with a lot of people on and kind of a lot of stuff that we want to look at, we won't necessarily be able to do as much synchronous interaction. So All right. The agenda here. So we'll talk a little bit about Ray, a little bit about AnyScale. We'll try and keep that to like the next 10 minutes or so, like not too much time. Then we're going to get down into some actual code. So today we're going to focus on Ray train, which if that doesn't mean anything to you, it will, I promise. It'll mean something to you in about 5 minutes. But it is a library that is part of the Ray ecosystem, and it's focused, like it sounds, on model training. So we're going to look at two actual examples with that. One, training a kind of a simple deep learning model, but doing it with PyTorch Lightning. So kind of looking at what is the same as your regular PyTorch Lightning workflow, and then what has to change in order to run this stuff with Ray. And then we'll look at another example with just straight PyTorch. So I would say these days, most people that are doing stuff with PyTorch are doing it with Lightning for various reasons, or maybe even something higher level, like more abstract, like Hugging Face. But sometimes to get a good understanding of what's going on, it's also handy to get kind of a little bit closer to what's going on underneath the hood. So doing an example with just pure PyTorch, so you can see that there's no magic there. And we'll also introduce into that example a little bit of a library called Ray Data. And like it sounds, Ray Data is about data ingestion and processing. We'll talk more about that in a couple of minutes. So I see there are a couple of great questions, one about training, one about Ray Summit. So we'll definitely circle back on those. I'm going to hold most of the questions till the end, so you can see there's a little entry on the agenda for Q&A. So we'll definitely get to that. So what is Ray? I said something earlier about Ray being an easy and fast platform for doing distributed computation. So that's kind of like the one level, sort of one line elevator pitch kind of a description. Here's a little bit more information. So we can separate the Ray platform at first into a couple layers. There's kind of a bottom layer, which is sometimes called Ray core. And in the picture on the right-hand side of this slide, you can see that there is a kind of a blue box called Ray core. So Ray core was the original kind of kernel or central part of the open source project. It was built out by a graduate team at UC Berkeley starting several years ago. And the idea for Ray core is to create a really high performance but simple infrastructure for doing scale out distributed computation. If you've been in the industry for a while, you may think, wait a second, I think I've heard the story before. Aren't there lots of these frameworks for doing high performance distributed computation? And the answer is yes. And what makes Ray core interesting is that it's designed to be more flexible than some of those other ones. So it basically can do any kind of a program, not just certain specific patterns. And it's designed to accommodate certain requirements like stateful actors and things that some of the other platforms were not designed to handle. It's also designed from the beginning to support heterogeneous hardware. So the folks working on this had some pretty good intuition that sooner or later we'd all be using CPUs, GPUs, TPUs, IPUs, different kinds of processors that were not the same hardware. And so we would need a way to build systems that didn't assume you had a symmetric cluster, right? So a lot of frameworks assume that every piece of your cluster has the same hardware and configuration and everything works. But as soon as that's not true, things get really complicated. Ray was designed from the beginning to support heterogeneous hardware, and specifically these days, things like GPUs. That turns out to have been a really good design decision. Above the Ray core, there's another layer. That's this teal-colored box in the picture on the right-hand side of the slide that says Ray AI libraries. So this is a collection of higher-level APIs for simplifying common use cases. So Ray core you can do anything with, but it might take a lot of work because it's a very simple set of computation primitives. If you just want to do something like grab a chunk of data off disk and train a model with it, you don't want to have to reinvent that wheel from low-level Ray core code. You want to be able to do this in a few lines, just like you're used to doing with things like Torch Lightning. Or before that, things like scikit-learn. So Ray AI libraries gives you high-level APIs, so literally, in a lot of cases, just a few lines of code, for common use cases like ingesting data, transforming data, training a model. And the idea is that they are implemented internally using all of the Ray core best practices to give you the best scaling and performance. The four that are listed in the picture on the right here, Ray Data, for data processing, Ray Train for training models, Ray Tune for hyperparam optimization, and Ray Serve for serving models. There's also a couple of other libraries like RLlib you might have heard about for doing reinforcement learning, but the four main ones are on this picture here. Okay, so why would we be interested in Ray? I think I've talked about that a little bit already, right? So Ray's strengths seem to align really, really well with exactly what we need for high performance training, inference, and data proc for large AI models. And it's interesting because that was not exactly the original idea. 6, 7 years ago when the team first created Ray Core, they just thought, well, it would be really great to build something kind of super scalable, super high performance that handles all these features. And it turns out that as the industry evolved towards the kind of AI models we're working on today, that's a really, really good fit. So it's kind of being, a little bit of luck of being in the right place at the right time with these capabilities in engineering. Over on the right, so why AnyScale? So if Ray is so great, why do we need something else? Why don't we just download Ray, which you can do. You can just do a pip install Ray and get Ray completely for free and run it locally on your own laptop. It runs great on even a single machine as well as on big clusters. And the thing is this, Ray is great open source software. It does lots of cool stuff, but it's focused more on performance and simplicity and capabilities. So being able to do things, from the point of view of like AI engineering, AI training, but not necessarily from the point of view of enterprise infrastructure. So once we've got this cool project running on our local cluster or on our kind of private Amazon cluster, wherever we happen to be running it, and we convince our bosses that, hey, this is actually the solution we want. We want to go put this thing into production and run it on at scale, where the whole business depends on it. There's just other stuff that we need that lives outside of the core Ray library. So, all of that operations stuff. And that's where AnyScale fits in. So we'll talk a little bit more about what is in AnyScale. I kind of think about it as 4 layers. I don't know if that's kind of the official way to break down the platform, but it makes it, I come from a kind of a software engineering background. And for me, this is kind of a good way to think about it. There's the infrastructure layer, the service layer, some enterprise features, and then kind of bonus stuff, technical features and extensions to Ray. The infrastructure layer are things like managing your clouds, right? Like you might say, hey, I want to have a cluster that's got 32 nodes and it has 24 of them have got 8 GPUs and 8 of them just have like CPUs, and I want them to have certain kind of performance characteristics. Well, we're going to need something to actually go and acquire those nodes from Amazon or GCP or whatever, make sure all the networking is set up, all that kind of just boring stuff, but it has to happen. Managing these hardware environments. If you build a hardware environment that's configured for your application, you may want to reuse this, like for development for other systems. So we'd like to be able to record this. We'd like to be able to version it and not be doing things by hand or having to like throw a lot of scripts around. So AnyScale manages these and calls them compute configs. Cluster environments. Basically, this is your software environment. So you're going to be using Ray, you're going to be using AnyScale, but you're probably also using a ton of other libraries, open source things like Torch and Lightning and Hugging Face, but also stuff that's coming from inside your company. And you're going to have specific collections of those libraries that work together, maybe other assets that you're depending on. And again, you want to be able to manage those things and version them. So there's infrastructure for that. If you create a cluster, you want to be able to kind of manage this cluster over a long lifespan, meaning configure it and get the right assets onto that cluster in terms of storage, and then be able to stop it. Say when you don't want to spend money on those GPUs, you go home for the night. If you're doing development, come in the next day and turn it back on and have everything where it's supposed to be. So different kinds of storage scopes and having an identity associated with clusters, especially for development purposes. And so one of the things AnyScale gives you is a set of scoped storage systems that kind of have different lifespans. So a really fast local only storage scope that's handy for caching things so you're not always getting them from other systems or from the internet. A cluster scope. So as long as a cluster exists within the AnyScale system, as long as it has an identity, even if it's not turned on, you get automatically a POSIX compatible shared storage that's visible just within that cluster. This is extremely, extremely useful because a lot of times in any kind of distributed compute, we need some file system that everyone can see, kind of looks the same way. You can always use things like, S3 buckets, stuff like that, but that's not quite the same as a POSIX file system. It doesn't perform the same way, and it doesn't really have the same features. So it's nice to have that. There's also storage scoped to the user. So you as an individual user, across anything you're doing within AnyScale, you've got a file system. And then your organization, which could be your whole company or a business unit within your company, can also segment a file system that way. The next layer, we've got the service layer. So these are services that AnyScale offers kind of in addition to, and beyond what's just basically in Ray. So one of them is Workspaces. These are a collection of a hardware cluster, a software config, and then a development experience that includes things like Jupyter Lab notebooks or VS Code, a dashboard where you can see what's going on. And we'll actually do the code later in the session today using a workspace. So you'll see that live. Job management is basically a way to schedule and run things that are not interactive, right? So a lot of your production workloads, it's nice to have interactive when you're developing them, but in production, right, you don't want to be like running a notebook in production. We've all had that kind of debate before. You want to be able to take a script that you built and tested and then be able to schedule it, run it. And so when we kick off an AnyScale job, it's associated with resources and software, and it kind of builds up its cluster and sets up an environment, runs, records all of its results, reports back to you. So we can do productionization of workloads that way. And then AnyScale services. So Ray Serve, which is the component of Ray for serving models or other chunks of compute logic, we can actually use Ray Serve to create services that are exposed to other software or even onto the internet. But AnyScale services adds even more production capabilities on top of that. So things like versioning and like canary rollouts, green-blue rollouts for routing traffic between evolving versions of systems, and things that are a little more sophisticated for actual production scenarios. Then we have enterprise features. So these are maybe not the most exciting from a software engineering point of view, but they're really, really important for successful system deployment. So admin stuff, operations, and security. Things like keeping track of who's who, so single sign-on support, granular access controls, audit logs, if you need to be able to know who did what when. These are all really, really important things. And then the last piece are additional technical features and extensions kind of beyond Ray. So some of these things may end up in open source Ray sooner or later, but right away, they're available through AnyScale. And these are things like enhanced data processing support for video and audio, access to Databricks if you've got stuff in the Databricks Unity catalog, access to Snowflake. Your company's probably using Snowflake for something. And some other integrations, things like faster local storage so that we can kind of use some really fast local storage in place of having more RAM or pushing stuff to a more distant storage, things like that. And like I said, you can try this right away. So if you go to AnyScale.com, you can sign up and start without a credit card or anything. You can just start, and then there's a chunk of compute credits you'll get right away. And there's some templates you can try, which I think are on this next slide here. So if you get started and you're thinking, well, okay, this is cool, but I have no idea what the heck I'm doing, you can literally click one of these buttons and start with an example like deploying a language model, fine-tuning a language model, deploying Stable Diffusion. That's one of my favorites. That's kind of fun because you get to generate pictures right away. Fine-tuning Stable Diffusion. So that's kind of an interesting project. So there's a bunch of templates you can start with, or lots of other stuff online. So I'm going to dive into the actual live coding section here in a moment. You can see I've hidden behind here on my desktop this web browser, which is pointing at an AnyScale workspace. So in this tab, I'm looking at the AnyScale workspaces list for one of my accounts here. You can see I've got 3 workspaces I'm not using right now that are for different development projects. So one that says Dev May, one that says Dev June, another Dev June 2. Those are turned off right now. And then I have this one that's active right now that says fast and scalable model training. So I can create different workspaces for different things I'm working on. And I've got a Jupyter Lab view into the training one right now. Before I jump into this, though, I want to take a quick look at some of the questions. Let's see, there's a question, does AnyScale offer online training? We do have a combination of some in-person training and live training. And if you contact me, so Adam B at anyscale.com, we can get you some more information. Or if you look on the AnyScale website and contact anyone in sales there with your interest there, we'll definitely get back to you. Grants for attending Ray Summit. That's a great question. I don't know the answer to that, actually. So I would say that would be something we need to follow up on. Building end-to-end ML pipelines, kind of like with SageMaker. So short answer, like, yes, you can do very, very similar things. We're not going to do a complete end-to-end today, but yeah, there's some stuff about that on our website. There's also tons of examples in some of our other online sessions and at Ray Summit. But yeah, you can absolutely use Ray and AnyScale as an end-to-end platform. Let's see, another question. If I use AnyScale in Google Cloud, does that enable fast multi-node trainings, do any setup? So the short answer is yes and yes. So we'll see some of that here today, right? So we'll get into more of the details, but yeah, the whole one of the whole benefits of Ray is that we can do arbitrary scale out. So if you think about how you scale model training, right, you start out with like a GPU, and then you can scale to a node with a bunch of GPUs. But like in this particular question, at some point, you're going to want to go to multi-node, where you've got lots of nodes with 1 GPU each, or maybe lots of nodes with lots of GPUs each. And getting everything running for that can be, and kind of maintaining that can be a little bit tricky. That's exactly the use case that Ray Train was designed for, is to make that really simple. So yes. Let's see, there's another question about syncing the POSIX file system or loading data into it, and can you sync with buckets? Yeah, it's just there for your convenience. So you can absolutely do anything that you like with it. You can write scripts that load data in there. You can also move data to and from buckets. Maybe a better way to say this, because this question's come up before, is Ray and AnyScale are not constrained to that file system. It's just there as like a free bonus that's nice to have. So if your current training scripts load things from Google Cloud or from S3 or from someplace else in your company, that will all still work. So none of that goes away. It's just that sometimes it's also nice to have these other file systems. So it's kind of a bonus. You don't have to actually change anything, but you can totally do that if you want. Let's see, a few examples for end-to-end pipeline. We're not going to have that today just for time reasons, but we'll try to get to that in a future session. Let's see, some of these are more technical. We'll save for the end. Just looking at some of the, I think we'll save the rest of these guys for the end because they get into more technical things. Okay, so let's take a look. We've got 2 examples. You can see on my screen here, there's kind of 2 notebooks, and I mentioned that earlier. We're going to do a Lightning one, and then we're going to do a data and PyTorch one. So the scenario we're looking at in this first example is, imagine that you've been developing with Ray Lightning. So you've got a Lightning data module, maybe that wraps your data ingestion. And you've got a Lightning module, like a classic Lightning module, that wraps your model structure, and then the training hooks. And your challenge is, okay, I want to scale this out. I want to use it with Ray. How do I do it? So we want to look at migrating this from Lightning to Ray Train. Now, in this example, we're just using Ray Train. So it says here without Ray data. And I want to make that distinction because in the other example, we're going to add Ray data as like another useful piece. But here we want to keep it kind of as simple as possible. To keep this really small and fast for training, you can see we're just doing MNIST here in terms of a data set. It just keeps things nice and simple. Everyone knows what it is. And it will run really quickly. The MNIST data set that we're using is actually just the one that you would grab from Torch. So you can see up here, I've got my Torch Vision datasets MNIST. That's where the actual data is going to come from. And it's implemented as a Lightning data module. And there's nothing that's Ray or AnyScale specific in this data module. So this is completely compatible with whatever module you're currently, or data modules you're currently using. There's no, you can see there's no Ray in here anywhere. There's no AnyScale in here at all. This is just a classic Lightning module here. So we've got some initializer, we've got some setup, we can produce train, validation, and test data loaders on these calls, and that's pretty much it. So we'll go and evaluate that cell here. Then we're going to do our model, which is our Lightning module subclass. So this will encapsulate our model itself as well as the training steps. So for the model itself, we're just going to use something really simple, again, just to keep it kind of minimal. But if you're wondering, like, what happens when this gets more complicated? The same basic structure works. So one of our big projects that we worked on with a customer that you may have heard of named Canva was training Stable Diffusion from scratch. And that is done using Lightning modules and Hugging Face. And it's basically just a slightly more complicated version of what we're seeing here today. And they're using it to train Stable Diffusion in production from scratch. So much, much bigger, more complex model, a lot more data involved, but the structure is, almost the same as what we're demoing here today. So we've got a little model here. We've got a couple of config things for setting up things like learning rate, keeping track of losses, accuracy. We've got our training hooks, and this is just the regular Lightning stuff. So again, there's nothing that is Ray specific here. So this is your usual Lightning code. You have to define a forward. You're going to define a training step. If you're going to do validation steps and or test steps, you're going to define those. Usually there's some shared logic there. So you probably come across this yourself in Lightning, that you're going to write some kind of shared logic that's used in more than one of these steps, so you don't have to repeat yourself. And then we can put hooks for things like on validation epoch end for collecting statistics. And then, of course, configure optimizers. So that's like an essential part of Lightning and how you tell the framework what optimizer you're actually trying to use here. So that's going to be our Lightning module. So far, we haven't done anything that had Ray in it. So let's get to the Ray part. So what has to change? What has to happen here in order to use this with Ray? So the biggest thing that has to happen is we're going to take the code that normally would instantiate our models and our data modules and our Lightning trainer, and then do our Lightning trainer.fit. We're going to take that logic, and that's going to have to run on every single worker. So what we're going to do is we're going to put that into a function that's called the per worker training loop, or per worker training function. And that happens in this cell in the notebook right here. So we define a Python function. This one's called train func per worker. Maybe not the best name, but the idea is this is the logic that's going to end up getting started on every single worker. So in the Torch distributed world, that's usually going to be a worker process associated with each GPU somewhere in the cluster. There are some other patterns that can happen, but that's the most common. And what's going to happen in here? So inside of here is almost just the regular Lightning code. So we get our model, our Lightning module right here. We get our data right here. We configure our Lightning trainer. So the Lightning trainer is mostly standard. There's a couple of little adjustments. So some things are normal, like CSV logger or weights and biases if you're doing things like that. Accelerator, configuring epochs. Okay, so what is different? So what's different are these three guys here. So there is a strategy we're going to specify called Ray DDP strategy, and that stands for distributed data parallel. So this is going to help integrate Lightning with Ray. There's a plugin, Ray Lightning Environment. So we also need that. That's also for completing the Ray and Lightning integration. And then there's a callback, Ray train report callback, and that's just for synchronizing the metrics and data that's coming out of those worker processes back into the kind of main Ray process, so that we can do things like keep track of statistics in case we want to do, like, say, early stopping, or we want to do checkpointing, right? We need to get some communication back into the kind of host process. So we're going to plug these 3 lines in here. Then we're going to make this call, prepare trainer, and this is going to give the framework an opportunity to adjust this trainer if it's needed to get it to work with Ray. In some cases, there's some adjustments here. In other versions and for other frameworks, not too much happens in the prepare trainer, but it's a pattern we follow, so it's a best practice to always call prepare trainer. And then we just do our trainer.fit. And we're passing our regular, so just to be clear, this is your standard code. So the lightning trainer.fit, lightning module here, lightning data module here, and then the same thing here with tests. So nothing else changes. And let's see, let's go and evaluate this cell here. We're going to do 2 workers with use GPU set to true. We'll evaluate our train func per worker. And now we're ready to go and get everything ready to do our training. So to do that, we're going to orchestrate everything using a torch trainer, which is a class in the Ray framework that handles training for all of the PyTorch related tools. So if you're using PyTorch directly, if you're using Lightning, if you're using Hugging Face with PyTorch models, in all those cases, you're going to use a Ray torch trainer. And the API for this isn't too complicated. You have to tell it what to run on all the workers. So we're going to put that train func per worker in here. We have to tell it how big to scale the cluster. So we're going to pass in a scaling config here. And you can see that has to have at least how many workers, and whether we want to use a GPU. And then we're going to pass in a run config. The most important thing in the run config, and the only thing you really, really need, is a piece of shared storage where all of the workers can see each other's storage in case they need to write checkpoints and statistics and things like that. And that's the storage path here. In order to show off a couple of other features, this particular run config has a couple of other things. It has this name, which is going to end up in the statistical reports, experiment reports that come out of the training. It's also got a checkpoint config, so we can tell Lightning to do things like, hey, we're telling Ray to do things like, let's keep checkpoints, but don't keep all of them. Just keep the 3 that have the highest score in the validation accuracy statistic. So you can kind of customize how your checkpointing works. So we'll get that set up. And then we're going to do a trainer.fit on the Ray trainer, the Ray torch trainer. So let's kick this off, and we should see some distributed training happening. So we've identified our resources, and now we're starting to use them. So we're using 1 CPU and 2 GPUs. You can see here that we've got A10Gs that we're using. We're getting some updates printing out here. I would show you the Ray dashboard. I can go to open it, although I think what's going to happen is that this training is going to finish so fast that before we really get to see anything on there, it'll probably be over. Yeah, so I think this thing is finished already. Maybe see if I can get the dashboard set up for the next demo. But the idea here is we've now run a training using PyTorch, using Lightning, using distributed data parallel across 2 physically separate machines. So going to that question earlier that we had in the Q&A about, does Ray help do any setup? You can see that I didn't personally have to set up anything for this. Ray set up all the communication. Well, it uses PyTorch to do some of that work, but Ray and PyTorch together set up all the communication. We're running across 2 physically separate machines that each have an A10G, and we're working together and producing a single model output. Here we can see the stats on that, and we can see where it physically is. So in this path here, which is another reason why having some shared storage here is nice. So in this path is going to be a regular old Lightning model, which is really a torch model that represents the result of our training. There's also, other checkpoints saved as well. And just to show that we can load this up, so let's say I've been using Ray to do some massive training project, and now let's say you're working on a project where you don't care about the training and the model's not that big. You just want to load up the model and use it for some use case for your job. So it's a regular old Lightning model. So you can just take the Lightning module class and do a regular Lightning load from checkpoint and point at that file, and you've got your regular old model. So there's nothing Ray specific about the model either. You're not like, you can work in the Ray ecosystem, but you can also just take these things and work with them elsewhere as well. It's just a regular Torch and Lightning model. So okay, cool. So that hopefully made some sense. Hopefully it was a little boring because you're like, hey, that wasn't very exciting. Where's the magical Ray stuff? And if you're thinking that, that's the whole point. So the idea is to make this as straightforward as possible based on the tools you're already using, not to create a whole new system, with tons of new APIs that you have to learn. Let me take another quick look at the Q&A and just see if there's anything that we want to specifically talk about with respect to this. And again, the other questions we will answer, but we'll hold for the end of the session. Let's just see if there's anything specific for this. Okay, so probably not anything very specific to this Lightning piece. There are lots of great questions, and I will talk to them. I'm going to hold those because they're generally useful for the end there. So we have one other demo notebook that we want to look at. So this is also a very simple model using a very simple data set. So we're not going to see any exciting AI here. We're not doing stable diffusion just yet. This is a simple tabular processing kind of perceptron model. And the data is some of the New York City taxi cab data, which you may have seen before in some other demos or blog posts. It's just some tabular data. What we want to demonstrate here are two things. One, using Ray Train just with PyTorch. So maybe you've never used Lightning, or for whatever reason you'd like to see this without the Lightning layer involved. We can see a little bit more maybe what's going on just looking at Ray and Torch. And we're also going to introduce Ray data just a tiny bit to show where that might come in, right? So in the previous example, we saw that if you're using Lightning data modules or Torch data sets, Torch data loaders, all that stuff works. But it may not be the fastest way to do this stuff at really large scale because you may run into situations where you want to do like some transformations on say your batches of Torch data, and you want to distribute those transformations in like an intelligent way, like using specific resources or using other models to do those transformations, things that get a little more complicated than maybe just like a Torch vision normalizing an image kind of transform. So for situations like that, where we want to ingest and do some processing on data at scale and then feed that into training, we have Ray data. A really common example of this right now is generating embeddings. So there's lots of applications today that are generating embeddings for text, for LLM-based applications, or embeddings of images for doing things like image fingerprinting or multimodal stuff, where you want to create these vectorized representations of images or text. And so that counts as pre-processing, right? That's not super hard. We've got kind of pre-trained models for those, but it can be kind of heavyweight. We want to, keep those models running and, associate them with suitably performant hardware. So maybe a GPU, but not our fanciest GPUs, because maybe the fanciest GPUs we actually want to use for the main model training or inference. So they kind of, represent a real world example that gets a little bit more sophisticated. So we won't see that in this example here today, but Ray data works really well with that pattern. Okay, so let's run some code here. How do I get some taxi cab data? So I'm going to go ray.data, and then we've got read APIs for lots of different formats. So, all of your common data formats are supported here. Parquet generally is one of the best performing ones for especially tabular data, but even tabular data with embedded binary data, it works really well. We're loading it from an S3 bucket. So this is an example of something I mentioned before, that local POSIX file system. Those extensions are nice, but everything doesn't have to be in there. Here we're just loading from S3. Ooh, I'm missing some imports. Let's do the import at the top, and then we'll do this read parquet again, and this time I think it'll be a little bit happier. So like in some other large-scale data processing frameworks that you may have seen, things like Apache Spark, the Ray data abstraction is designed to handle arbitrarily large sets of data and to process them in a lazy way. So we're not going to go and like read all this data into memory and then start poking around on it like we might with pandas. Instead, we're going to create a recipe for kind of flowing this data or streaming it from a source, doing things with it, and sending it somewhere, because that's the trick that allows us to optimize and to work on really, really large data sets. So what are we going to do with this data? What's interesting here? Well, the main thing we have to do is just convert all of these values into kind of vectors from the individual columns, and then stack them together into matrices for training. So we'll just look at some code that does that. So here we're going to take a batch of records from this data set and kind of look at it. So you can see we've got some columns and they're each associated with some vector of values. There's some different types here. What we want to do is rearrange these and kind of stack them up into a matrix for deep learning training. So we're going to go and grab the values. We're going to go and convert these to lists, stack them up. So this is just a little bit of NumPy kind of playing around. And then if we do a transpose, we'll get them in the right orientation where we have the records or batch axis and the zero axis, and then the features in the next axis. So where does this connect to Ray data? Well, if we have a program, this is a very small program, but it's a little program that does some data transformation, we can run that over our large data set by putting this into a function and then calling map batches with our data set and providing that function. So now what we can do is we can run batches of data from our data set through this transformation. And the cool thing that we can do with Ray data is if we have a transformation like this that is stateful, like let's say it loads up a big expensive model and we want to keep that model around to do lots of processing, there's a version of this that looks a tiny bit different where we can use a whole Python class that is allowed to have kind of arbitrary state, like loading a model and doing other things. And we can route our data through that, and we can have multiple instances of that. It's called an actor. We can have multiple instances of that actor, and we can spread our data processing across those instances, across our cluster. And you can see how those couple of things working together give us a lot of scalability and efficiency. The statefulness, being able to allocate hardware like GPUs for this processing, being able to run lots of these across the cluster. So that's kind of the pattern that looks like. This map batches that we're seeing right here is kind of maybe one of the simpler flavors of data transformation. Okay, so let's go and do our training, right? That's all. We've got our data prepared. If we want to do our training, once again, we're going to write a per worker training function. And this is going to be the process that gets started on every worker. And in this example, it's called train func, so it doesn't really matter what we call it. You could see the other notebook had a different name. And it's going to get this config variable. So anything that we want to pass, small values, not big data sets, but small values like hyperparams, for example, that we want to pass from our main control process into the per worker training loop is going to show up in this config. So that is another kind of convenience mechanism for getting things that we decide in our main program automatically distributed into the right workers. So we don't have to come up with ways to like get all that stuff into the right place. So what are we going to have in this per worker training function? So first we're going to set up a model. And here you can see it's just very basic torch NN sequential with some layers. I'm doing some of those layers shape based on values that are coming in from this config. So you don't have to do that, but here I'm just demonstrating how we could have maybe make some decisions about the shape of our network in our main process and then have that get propagated so that it automatically comes up in the right place and our individual models are configured correctly. We've got our loss function, our optimizer. We're going to do a prepare model on our model. So when we're working with a model directly like this in Torch, and we use it with train, we're going to pass it through a call to Ray train torch prepare model. So this is similar to what we saw with the trainer in the other notebook. It's a best practice to pass this model in. It gives Ray a chance to put hooks in or make other adjustments that need to happen. If you've used Torch data parallel before, you may remember that there's a similar call you have to pass where you take your Torch model and pass it to Torch to DDP to generate the data parallel wrapping. That's kind of what's going on here. If that doesn't mean anything to you, don't worry about it. Then we're going to go and grab the data set. So I said the config is good for small values, like say the H1 width, which is what it's like 10 or something like that in here, some single number. What about a big data set? So the way we're going to do that is we're going to use a couple of helpers from Ray. We're going to call getDataSetShard, which will get us a disjoint slice of our big data set just for this worker. So if you have lots of workers, they're not all using the same data. And then we're going to call iterTorch_batches to pull chunks of data off of that shard, convert them to PyTorch tensors of a particular type and a particular batch size. And then we can just walk this training iterator right here and pull off batches and do regular old training. So here is a simple PyTorch training loop. We're going to do 5 epochs. We'll get our batches from this training iterator here. We're going to slice up our features and our labels. We'll calculate our outputs, our loss. We'll do our zero grad. We'll back propagate. We'll update our weights with the optimizer. And that's just your usual PyTorch loop. Then we have a little bit of code specific to reporting checkpoints. So if we want to record checkpoints, what we're going to do here is figure out which is our number 0 worker. And for that worker, we're going to record the current model using a regular torch.save. Why we're using just the one worker? Because in DDP training, the model's the same on every worker. So if we have like 30 workers, it doesn't make sense to record 30 copies of the same model. We just record the one. We're also going to report our metrics back to Ray. So we'll go and get this running. Then we're going to set up our scaling config and our torch trainer, kind of like what we saw in the last example. And then we're going to do a trainer.fit. Before I do the trainer.fit, though, I want to call attention to, let's see, 2 things that are new in this example. So before we saw this, per worker training code, we saw scaling config before. We saw run config before. That's the thing with the shared storage. Here we're passing Ray data sets. So we could pass as many as we want, train, test, validation, extra data, however, it doesn't matter. We can pass as many as we want. We put the handles to those Ray data sets in this dictionary, and then we can access them using this call inside of the per worker training loop. So by name, we can get a shard of any of those data sets. So that's relatively straightforward. And then for the small values, I talked about that config. This is where that config dictionary comes from. So this allows me to specify values in my main code here that will propagate into my workers. So let's go and get this running and see if it wants to train. And this is, not a super complicated problem, so it'll probably finish in about 20 seconds. Looks like it's already done. And if we look at this result, so here is our output. So we had a loss of, this score here. This is where our last model is stored. And we've got a checkpoint object that wraps that model snapshot. So we've successfully trained that using our cluster. So yeah, it's so challenging to do these examples in like a 1-hour setting here because we're almost out of time, but we've got a few minutes left for the questions. And I know I've been promising that we talk about these questions. So let's do some of that before we wrap up here. So let me take a look at which questions we haven't answered. I'm just going to go back to the beginning and take a look. Okay, so I think the first one that we haven't talked about yet. So if I have the question is, if I have a large data set, hundreds of terabytes or petabytes in S3, what's the fastest way to load my data into a Ray data set and iterate it through it in batches? Great question. And the answer is something very much like what we saw in here. So the simplest way is create a Ray data set that looks like this, and define whatever transformations you may need to do using either actors or functions, so you can do things like map batches. But in terms of iterating through it in batches, you can, if you want to just process it in batches kind of without training, you can do it like this. So you can do things like map batches, which will, process it a batch at a time, and you can configure things like how big the batches are and, the resources associated with that and all of that. If you want to get those batches specifically for training, like maybe you don't need to do any transformation or you're already done with that, it's going to look like this pattern right here. So you're going to get a data set shard on the worker, and then you're going to do an iter batches if you just want raw batches as like whatever the original data flavor is, or iter torch batches if you want torch tensors. And this does work at scale. So like this is what we use for stable diffusion on a much, much bigger data set. It's the exact same code. Well, I mean, not literally the exact same code. It's the exact same pattern. And that works pretty nicely. Let's see, what else do we have here? Let's see. How do we virtualize the compute resources for each node? Okay, so yeah, so in the AnyScale and Ray system, there's there's kind of three flavors of that. So mainly we're going to have individual worker machines that are going to be, like if we're in AWS, they're going to be specific AWS like EC2 node types. So those are, there's some virtualization going on the Amazon side, but we treat them as like physical servers basically. So that's one layer. There's another layer in terms of, let's say you've got one of these instances and it has 2 GPUs on it, but I've got some code here in Ray that is, needing different numbers of GPUs. How does that work? So the way that works is Ray has its own capability for accounting CPUs, GPUs, other kinds of accelerators, or custom resources. So you can, in this example today, the only thing we did that involved something like that is where we said scaling config num workers equals 2. But there's a lot more fancy things you can do. You can write individual pieces of your code that say things like, I need 1 GPU and this many CPUs, or I need a GPU, but I don't really need much of it. So I'll take 1/10 of a GPU because what I really need is the compute capability there, but not much of the memory. You can also define custom resources and other kinds of things, and Ray will do the accounting for that and make sure that stuff gets scheduled in the place where those resources are present. If those resources don't exist in the cluster, but auto scaling is available, then Ray and AnyScale can scale up to acquire those resources. There's one more level of virtualization that's used for certain edge cases where we need like different software environments for different pieces of code. But I don't want to get into that today. It's a capability that is really cool, but it's just maybe a little bit too much time for today. Let's see, what else do we have here in terms of questions? There's a question about a Bastion server with Slurm. I don't have an answer for that today, so I don't want to talk out of turn and maybe take up anybody's time with my bad guessing of that. We'd have to get some other input on that. Integrating RAID jobs with Kafka for large scale testing. So yeah, you could certainly integrate Ray with other, it's just Python. I mean, that's, the deep engine of Ray involves C++, but all the programming of Ray that you're going to be doing involves Python. So it's pretty straightforward to integrate it with other systems, and you can absolutely do that. Can Ray work efficiently with Triton and other inference servers? Yes. So there's a few different, I think there are implementations of that. I think AnyScale has one, but I'm not 100% sure whether that's the current one that we're deploying, but it's been built, and those things are around. Let's see, what else do we have here? Some great questions. How do you define the storage path for shared memory in a cloud environment, for example? So the storage paths that are built in, they're like, they are basically at fixed paths. I can show you what that looks like. So you get, so for like cluster, So for like cluster scope storage, it's going to look like this. So /mount/cluster storage, and you can put whatever you want underneath there. So that would be for cluster storage. If you wanted something that's for your entire organization, but scoped to you as a user, that's going to be under like user storage. So here is anything I've put in on any of my work, I can see in here. So there's a bunch of different mounts that are kind of built in that way. And of course, you can always add more, but that's how the built-in ones work. Is it possible to define your own scheduling algorithms? So if you mean for like the core Ray scheduler, I mean, in theory, yes, it's open source and there's a lot of stuff you can configure. In practice, most people that are using Ray are using it because they already want to use the scheduling system that's been developed for Ray, because that's kind of a major investment in like research and development over the years. So typically they want to use that, but you can customize it. If you want to totally change its behavior, you can do that. It's maybe less popular to do it. Let's see. How does resource auto scaling work with Ray Train? Like if you run Ray in Kubernetes, can scale from 1 to 16 GPUs, will Train automatically scale up? So usually so the short answer is we can scale up the available resources, like the number of nodes in, say, a cloud environment or number of GPUs in the cloud environment. For the train task itself, we usually start with a set number of GPUs. So we want to have a certain number, like 32. We can scale the cluster up to get 32, but we usually don't change the number of GPUs involved in the training, just because the way the training algorithms work, they're usually they're usually expecting to have a set number of resources for the duration of the training. So if that makes sense, like there's scaling of the resources that are supplied to the training itself usually grabs a hold of a fixed pool. And then what Ray will do is, if we lose nodes from that pool, we can get them back. But we're not going to say, like, during training, we wouldn't typically scale from, say, 32 to 64 GPUs in the middle of a training cycle, just because the algorithms aren't really designed for that. Let's see, we're just about out of time. I'm looking to see if we have any more questions. Can you use Ray data and PySpark together? The short answer is yes, but it's a little bit tricky. I know that's maybe not a great answer, but it's tough. And the very last one I'm going to answer is, what do we mean by worker in Ray Train? So throughout Ray, when we talk about a worker, what we mean is a process that can run code and has some resources. So it can run your own Python functions. It can participate in a multi-worker distributed training process. It can participate in a distributed data processing application, but it's a process running somewhere in your cluster that has some resources and is running some of your code. That's kind of the definition for that. And with that, we're pretty much out of time. So I want to thank everybody for joining here today. Remind you to take a look. We'll send out the slides and the notebooks after this session. So there were questions about that. You'll get all that stuff in the mail. Definitely check out Ray Summit. It'll be really cool to meet up in person, and we'll all be learning more about Ray together at that time this fall. Thanks so much.